Okay, here is the Year 10 end of year exam, and hopefully this will be the answers. So, it's a 90-minute paper. I'll try and get through as quickly as I can. Here's the first question. It talks about a balloon, 8.5 meters cubed, and running at atmospheric pressure. It's taken to a height of, which is not really needed at the moment, but it changes its pressure too, so what's the volume? Okay, let's recall Boyle's law. So P1V1 is the same as P2V2. Quick rearrangement will show you that the second volume is P1V1 over P2. So what are the values? Let's plug them in. First pressure is 101 kilopascal, so technically we ought to put 10 to the 3, multiplied by 8.5 meters cubed, that's good standard form, and divided by the 40 kilopascals. I mean, actually those drop out, but it's good to place things in standard form in each case. And that gives us something like 21.5 meters cubed. 3 marks. Recall, substitution, rearrangement, answer, and probably for unit there as well, though they probably didn't look for that in that one. Okay, a second balloon is tethered to the ground, so it's unable to rise, but it's heated. Now, as we know, when balloons are heated, they actually expand. Because what takes place is that we have the pressure increases inside, and that means that the volume increases. And therefore, it reduces the pressure to stay even, if that made sense. So if this was contained and we heated it up, the pressure would increase. But the fact that the rubber can move means the pressure stays the same. However, the volume inside increases. And because we know that the density is the mass over the volume, and we haven't put any more gas in or out of it, if mass stays constant and volume increases, density must decrease. Good, okay. Now, the balloon rises. The first balloon rises because it's filled with gas. Okay, so why does it begin to accelerate upwards? Well, what's taking place here is you have the weight of the balloon, but also there's a buoyancy. And the buoyancy is greater than the weight, so you have a resultant force that's upright. So why does it? Because, terrible way to start a sentence, there is an upward resultant force. Okay, why is acceleration balloon reduces? Well, as this picks up speed, so not only do you get a weight, but you have a drag as well. So the drag on the balloon increases with speed. Okay, why does it eventually reach a steady speed? Well, the buoyancy, the weight, and the drag should all be equal, so the resultant force is 0. So why did there is no resultant force. What happened? What's it called when we reach a steady speed? Simply terminal velocity. Okay then, so trying to find the height means you need to recall this equation. Pressure is rho, density, times g times h, not to be confused with these two, of course. Pressure and density. Density is given, and pressure is given, and you need to therefore work out the height that has been gained. So let's rearrange to give ourselves height. pressure over rho g. And that gives us 101 times 10 to the 3, because remember in kilopascals, divided by 1.2 times, let's say g is as good as 10, 84200 meters. It must have gone up by. However, we know that density does not stay constant. In actual fact, we know that as we rise up, the density decreases. So therefore, what's going to happen here? Well, it means that the height will actually, if the density here is decreasing, the height will have to increase. So it will have to be higher. Okay, so quite a good question on that one. And leading into part 2 quite nicely, because it talks about density. So we've covered this already before. The equation that we need to know to measure density is mass divided by volume. And this one's asking to determine the density of the bath through experimentation. What instruments will you use? Right. Well, we need a balance to work out the mass. And we need for the volume, let's say a Eureka can. What will you measure and how will you use it? Well, the balance determines the mass, the Eureka can determines the volume, and the density is the mass over the volume. I think that really covers our 3 points nicely. However, what's happening here is that this balance, which has a weight on the end, is now submerged in water. What happens? Well, if you imagine this amount of water here that's being displaced, okay, the weight of that displaced water equals the upthrust that's being pushed up. So does the Newton meter increase or decrease when there is? Well, it decreases because you do have weight acting on the body. Let's just redraw this. But you also have upthrust acting on it. So what we'd say here is that, how do we explain it briefly and succinctly? Well, we would say that the water displaced equals the upthrust on the object, therefore reduces the weight. Good. What about the next one? Ice skates. I don't know whether you know this, but it's the pressure upon the ice that causes the melting of the ice that causes the frictionless motion. So a single skate has area, weight, mass, I nearly caught myself out there, and you want to determine the pressure. So the pressure is the force over the area, which is the same as the weight over the area, which is the same as mass times g, note, over the area. And it asks for it in newtons per centimetre cubed. So 60 times 10 gives us our newtons, and 5 centimetres cubed, thereby giving us about 120 pascals, or if you prefer, newtons per metre squared. Shows a bit more finesse to write pascals. Rearrangement, 1 to get the mass into the weight, 1 for the... and the answers. Okay, why might a small child not be able to skate an adult-sized skate? Well, once again, if you need a certain pressure to cause the ice to melt, and suddenly you have an adult skate which stays constant, the area, if the force goes down, the pressure goes down, so you might not melt the ice. Okay, just a bit of interpretation of reading the question carefully. Right, Brownian motion. We're given a picture here which shows a particle, water, and this random walk. That's the way it's going to one way. So explain how explain the motion of that pollen particle? Well, you should know from your revision that the invisible water particles, molecules, should I say, right, collide with the particle. This causes it to change direction. Now, in this case, because it's moving in this direction, you must have more collisions on one side than the other. But also, there are many, many collisions. It's not just one or two that happens over, it's many, many collisions. Okay, there's four good reasons, that's why I've put them in. Understanding Brownian motion can help explain other situations, explain why gases are able to react to pressure. Okay, so you have, again, a collision with gas on wall of container. Okay, that exerts a force, which in turn exerts a pressure. And you don't see sort of the container wall bouncing because there are many, many collisions. Many, many collisions per second. Okay, probably more than enough to get your 2 marks there. Question 5. No one works out in the gym. Notice it's hotter, heavy use. And then Ali speculates the extra heat is from the gymnasts working out. But there must be another source taken into account. This is a bit tricky, actually, because actually that's what most people imagine. It's the extra heat given out by the gymnasts. But what else could it be? Well, it's the chemical energy. Of course, it must be chemical energy in the first instance. And then you have the kinetic energy of the machine. Rowing machine going back and forth, cycle machine, you've got things moving. And the friction of the discs turns into thermal. And it's released. I think that's quite tricky, and quite tricky to get all the marks there. So let's make sure you get it absolutely right. Chemical energy to kinetic of the machine, and then the friction which that generates turns to thermal, which is released and therefore heats up. Here is an example of said machine, but it's asking some quite straightforward equations of electrical resistance, electrical power. Calculate the total resistance. Well, the resistance is voltage divided by current, and we just look, we have those two values. There's no trick here. It just tells you total amps and total volts, so 230 over 12 gives us something in the order of 19.2 ohms. 1, 2, 3, 4 marks. What's the power output? Well, once again, just an equation to memorize. Voltage times current, so that's 120 times 12, giving us 2760 watts. 1, 2, 3, 4. Sorry, I didn't even show that. What's the power? P equals IV or VI, 12 by 2. Fine, straight away. It's much the same as the previous one. Okay, but here we have an IV curve. Calculate the resistance, and you should know that that's a lamp. That's a characteristic IV curve for a lamp. What's the resistance at 60 volts? So 60 volts is here. 0.2 amps, so R. V over I. I know it's obvious, keep stating it in all cases. 60 over 0.2, giving you 120 ohms. What about at 200? Got two nice little values there that have been marked off for you. Once again, same process. This time we're at 200 and 0.4, giving us a grand total of 500 ohms. Why does it change? Well, the explanation for why this is a characteristic IV curve for a bulb is because as the voltage increases, so the temperature increases and the resistance increases as a result. So therefore the current doesn't come down, but let's say the change reduces. So whereas we'd imagine this line to keep going, for the same change in voltage, we're not getting the same change in current. So the change, so the change reducing is probably the way to describe that. Why does the resistance increase? I think that's probably worth expanding upon. We'll say the ions in the lattice vibrate more. And therefore, okay, so we are just talking about here about the reason why the resistance changes, and that's because as the voltage increases, we have a temperature that increases, and as the voltage increases, so the current increases, should I say, which means that the temperature increases. The resistance in turn increases because the ions in the lattice vibrate more, and that impedes the charge flow. And so rather than saying the current goes down, we should say the change reduces. Okay, good. So what's the next one? What does LED stand for? It stands for Light-Emitting Diode. Good, right. What changes, what energy changes are there in a filament lamp bulb? Well, we have the electrical energy goes to heat and light. So what you might think is predominantly aimed at creating light, about 80% of it goes to heat. Therefore, why is an LED more efficient? Because the LED doesn't create as much heat. Good, okay. Norman decides to investigate the IV curve. So what does he need? Well, he needs to know a voltage about the LDR, there's the symbol for the LDR, and a current going through the LDR. So in essence, that is what you're looking for. However, you're taking a range of values of current and voltage. Now, if this were connected directly, then the voltage would always be the same across the LDR. The LED. So therefore what you need to do is introduce another resistor which you can change. So there's a variable resistor, so that as you change this, so you're changing the current, which in turn changes the voltage about there. So that is your ideal circuit. Probably a mark for where the ammeter is in series, voltmeter, general setup, and also realizing that there are two components in there. Okay, number 6. You should all be familiar with this, the Rutherford experiment for working out the the model of the atom. Explain why it needed to be carried out in the vacuum. Well, if you see here, these are alpha emitters. There's an alpha emitter, and you should know that alpha is easily absorbed by air. Why was gold a good choice of target? Well, it's you can easily hammer it into thin sheets and chemically inert, which is very useful as well. So you know that it's not a chemical reaction that's taking place. Okay, let's talk about just briefly about our model of the atom here, so I can explain those observations. If there's our nucleus and our electrons flying around, and the alpha particles are coming in, because they're positive and we have a positive charge on the nucleus, there's an electrostatic repulsion that takes place. The amount of repulsion depends upon how close you are to the nucleus. So some of them will be inbound very close and get a large angle of deflection, and others that are not close at all will just carry on straight through. So really these statements are relating to each one of those. So So therefore, a small number of the alpha particle will deflect less than. Let's look at most is empty space, so the majority will not deflect it at all. That relates to this one here, the straight line. One or more were deflected by a large amount. Well, that suggests that the gold nucleus is very dense and small. And therefore, the first comment I had, some were deflected, is due to there being a positive nucleus. Good, so that was Rutherford. What would have happened if you used the plum pudding model? Remember there it was positive dough with these random electrons distributed was the idea. You'd get much smaller deflections occurring. Expecting smaller deflections due to positive dough. Okay, what's next? We're looking at alpha decay and the equation of alpha decay. Well, what here you'll need to do is you need to recall that alpha is 4, 2. It means that you have 2 protons, which are defined here. The top number saying how many particles do you have in the nucleus? Well, if you've got 2 protons and 2 neutrons, that will give you 4. Something just to remember. But with that in mind, then what you need to appreciate is this is like an equation along the top. So if that's an equal sign, 226 is 222 plus 4, and similarly 86 plus 2 gives you 88. So the number of protons, well, this defines the number of protons that you have. So that's easy, that's 86. Whereas the number at the top says how many particles you have in your or nucleons you have in your nucleus. So therefore, if we subtract from that the number of protons, that should give you 134 neutrons. Good. Radium is also an alpha emitter. What word describes its two forms? Well, look, radium. So it must have the same number of protons because otherwise it wouldn't be radium. But these numbers are different, so therefore it's an isotope, and there are 3 neutrons different. Because, I suppose to give a reason, because there are the same number of protons, but a different atomic mass. Right, we're looking at now how alpha radiation, whether it's beta or gamma, so we need a simple setup here. We need a detector, a GM tube, to detect radiation. We of course need the source, and then what we need to do is place in an absorber in between them. And that absorber will be aluminium or thin metal. Now, if it were gamma that were coming through, gamma would make it all the way across. So if it were gamma, you'd see no change. Whereas if it were beta, beta would be stopped by the absorber. So there would be a significant decrease. So that's the experiment. GM tube plus the source. You want an absorber and you want the observations. No change if it were gamma, because the gamma goes straight through. It was a significant change if it were beta. Okay then. Background radiation emission must be considered. How would you determine the level of background radiation? And what you'd do is you'd set up your detector with no sources and measure the rate. Then subtract that from readings. Remember, of course, what are the sources of background radiation? Mostly rocks in the Earth and cosmic rays. This is quite tricky to know what the background radiation count is, something you're just going to need to learn. It's about 30 to 10. You either know that or you don't. Okay, now with half-lives, because it's a random event, you ought to really take 3 values and average them, ideally. I mean, you don't have to always, but let's just try it anyway. Let's look at 40 to start with. There's a point. That's about 6 days. And then half of 40 is 20, which gives us 12 days. So the difference here is 6. Let's try the same again from, let's say, 60. So if we went 60, which is 2 days, and then we're going to go to 30, which is 8 days, the difference there is 6. So I'd say 6 days. However, as you see this curve decreasing, you'll see at this point here that it actually pretty much is flat, which means that you're no longer detecting the source, but you're detecting background radiation. Therefore, we'd say it's not dangerous anymore. So that's in part 2. Why the scientists agree that after this no longer considered, because it's the signal, sorry, the activity is less than the background. Right. Now we've got a use of radioactivity. It's used to sterilize packaged food. Explain why it is dangerous to living tissues. Well, the key word here is ionizes matter. Ionizes. Because if it's ionizing it, then it's doing damage. So it's damaging the DNA. And ultimately, if it's intense enough, it kills it. But ionizing is the key word there to use. Now, what do you want? Of course, this is an industrial process, and you're looking for something which will, first of all, get through the materials of the packaging. So that means those two are out. Beta might do it, not very well, but gamma definitely does. And also you want something that lasts long enough so you don't have to keep replacing it all the time. So excluding the alpha, 14 days, well, that's not really great. 28 years is better. 6 hours is definitely not going to work. 5 years is good. So our best option is cobalt 60. Here's a discussion going on between Norman and Ivor. Gamma radiation is most dangerous, whereas alpha is more dangerous. What happens here? Okay, so we need to first of all say that gamma is very penetrating. So doesn't ionize much. However, alpha is not penetrating, so ionizes lots. Okay, but alpha can't get, this is talking about bodies, I'm just checking, get into material easily. Oops, T. But if inside, does lots of damage. Whereas gamma can always get inside. So it is dangerous. They're not looking for you to really draw a conclusion here, they're just looking for you to draw out some important points here, because both are right in some cases and both are wrong in some cases. Good, I hope that makes sense. Number 9, interestingly, this won't be in 2015 end of year exam. We didn't have time to teach it, but I'll go through the ideas anyway. What's being illustrated by the process sheet is being described what's taking place. Okay, so you have a neutron. And that's being fired into uranium-235. Uranium-235 breaks up and produces 3 neutrons plus other bits, let's call them, which are not really needed. That's why they're not shown up here. But 1, that's the neutron, and they're producing 3 neutrons. The neutrons split other uranium-235, and it leads to a chain reaction. That process is called fission, nuclear fission. Okay, now, in the power stations, the reaction is carefully controlled using moderator, coolant, etc. Okay, so the moderator slows down neutron so it can be absorbed. Because, sorry, I should have shown that. Because this often is going too fast to be absorbed, it will just bounce off. So what moderators do is moderators slow these up to make them thermal neutrons so they can then be absorbed. What does the control rod do? Well, control rod absorbs neutrons to slow reaction. In other words, if we slotted in a control rod here, then all of those would be absorbed and only those would move on. And the coolant carries away heat energy to be converted into electricity. Right, okay, here is a question on Damien on his bike. We're going to be drawing this, so let me just take that out of the way first. There is the answer. But what it asks us to do is it asks us to turn to landscape and create the velocity time graph. So what you ought to be doing really is counting off the number of values you have and then working out what scale you're going to use, because really what you're looking to do is, when plotting a graph, is you're looking for the scale, you're looking to label the axes, make sure the correct way around, i.e. independent variable is going there and the dependent variable is going there. You then want to label them plus the units. You then want to have the correct points and then the line of best fit. So you think about those things first, and then when it comes to plotting your graph, you should get something that I made earlier, which looks a little bit like this. So note here about my scale, I couldn't get 12 to the top here, so I halved the scale. That's important. This one I got all the way up to 30, which is fine. So it says here, calculate the acceleration in the first 4 seconds. Well, this could be done from the table or from the graph. Let's look at either. The first 4 seconds, what's happening here is, well, acceleration is change in velocity over change in time. The change in velocity of the 4 seconds is 6 meters per second. It took 4 seconds to do it, so 1.5 meters per second squared. Note the unit, it's acceleration. Okay, now let's get to the last page, put it somewhere, back to here. So it's now asking for, what's the resistive force in this period here? Well, you know that there's a constant velocity. So therefore, the total resultant force must be 0. So we've got 280 newtons acting one way, then the other way must be 280 newtons. So the answer is 280 newtons. A car pulls across the path, it's 18 metres away, Damien brakes as hard as he can and stops just in time. The brakes apply for time. What's his thinking distance? Well, if it takes 18 metres to stop completely, of which 12 we use for braking, then that leaves us 6 metres in which I think about it and then do something about it. What's his reaction time? Well, therefore, the time is going to be the distance divided by the velocity. And we know that the velocity here travelling along at is 12 metres per second. And I know the distance from the previous one is 6. So 6 divided by 12 is 0.5 seconds. What's the deacceleration whilst braking? Well, the deacceleration is going to be, it's going to be the change in velocity divided by the change in time. And the velocity was travelling at was 12 metres per second, and the time taken is 2 seconds. So it's 6 metres per second squared. What about the average braking force? Well, again, F equals ma. 90 kilograms was given in the previous page, up here, and 6 from the previous answer, giving us a grand total of 540 newtons. And point C, when you notice the path, well, if it takes 0.5 seconds to brake, then surely here, that's where I start applying the brakes. So therefore, I must see it 0.5 of a second before, which gives me 21.5 seconds. Excellent. Now, the bit that I didn't do here was use the graph, find out how far to travel in the first 20 seconds. And for that, what you need to do is work out the area under the graph. It's quite tricky here. It's not an easy one to do. So what I did was I approximated. I said, okay, at this point here, I'll take the triangle, half times base, 8 times the height, 9.5. I then took this square, which is 9.5 high by 8 wide, 76 meters. This is 2.5 by 8 by half, giving me 10 meters. This square to 20 seconds, because it asks for 20 seconds. I think that's probably should be 22, but nonetheless 20 seconds, was 4 by 12.48. And that gave me a grand total of 172 meters. Okay, excellent.